Hello. I'm sorry the volume will probably not be as good and the reduced noise in the area just because I can't find my headphones. So what we're going to talk about is the test over physical and chemical properties, chemical reactions, and ways to affect the reaction rate of a reaction. All right. So in this section, the test will be over. This is a page that you have in your notebook. The first one starts with, remember those reactivity videos we had quite a while ago, the end of January. Then bonding, ball and stick models, and then we did electron dots. The lab metal or non-metal based on the physical properties of appearance and the chemical properties. Then the one where we actually did on February 13th, but it was comparing the reactivities of various metals. I remember how well you did on that. Then we started talking over a couple days on reactions fast or slow and the collision model about the reaction rate that talks about how fast and how energetic and how many more particles are having collisions is the basis of this idea about how we can increase the reaction rate. And then on February 21st, the lab to precipitate or not. So the first thing to get ready for the test is to complete the assignments in this section. I'm done regrading assignments from the first part of the unit, that is those below January 30th, but I want you to finish all the others to prepare and then watch the review video that I'm discussing right this very minute. So the first thing we're going to do is go to this first assignment, which is all the way down here. So this is one I have already graded. All right, and it's about the reactivity videos, and you were looking for the patterns connecting the reactivity in two groups. One is the column 1A, the alkali metals, and the other is column 7A. All right, we were looking at those two. All right, so we were watching those two videos, and from that, we were answering the questions about how do we test for reactivity, which halogen is most reactive, which alkali, what's the pattern, what's the connection in the two patterns and valence electrons, and etc. All right, so you took notes here after you watched the videos. All right, and I already graded this, I believe. Okay, so what we're going to do now is go over these, and so that if you didn't get them correct when we went through them, you'll have a chance to see them again. All right, and so instead of being this color, they're going to be black. All right, here we go. The first essential question was, how are elements tested for reactivity? So in the videos, you saw a group of metals tested with another reactant that they normally react with. Then you see which element has the highest reactivity in the group and which has the lowest reactivity. And hopefully there will be a pattern because the periodic table was put together to show patterns. The second question says, which halogen is most reactive and how could you tell from the demo? Well, the fluorine was too reactive to even show in the demos, so that's clear. That's very clear that fluorine is the most reactive of the halogens. Oh my goodness. All right. So we saw that chlorine was more reactive than bromine, and bromine was more reactive than iodide. With the two substances they tried, one was with iron and the other was with aluminum metal. The reactions were quite vigorous once they got going, so it was really clear which halogen was the most reactive. All right, fluorine at the top, least reactive iodine. Which alkali metal is most reactive? How could you tell? Well, cesium showed to be the most reactive element. All of the alkali metals reacted strongly in water, but each one down the column got progressively more terrifying, as the demonstrator said. And the demonstrators began to put more safety precautions between themselves and the reaction. You remember? All right, the pattern of reactivity up and down the column is the opposite from each other. So, for example, the halogens, the top is more reactive, fluorine, whereas the alkali metals, the bottom of the column is more reactive. All right? So, cesium is more reactive, whereas with the alkali metals, this guy at the top, fluorine, is more reactive. All right? So that's kind of an interesting issue, isn't it? What must that be about? Well, the smaller number of valence electrons that must be lost or gained increases the reactivity of both of these groups. So the question was, what is the connection between reactivity and the number of valence electrons? Well, in both cases, the alkali metals and the halogens, there's only one electron involved. The alkali metals want to get rid of one electron, and the halogens want to gain one. So that explains why they would be the more reactive groups of elements in contrast to others that have to have 2 electrons lost or 3 electrons lost, or in contrast to those who have to gain 2 electrons, who have to gain 3 electrons. All right, so the alkali metals with their 1 valence electron only have to lose 1, and the halogens with their 7 valence electrons only need to gain 1 to have the perfect. Therefore, the smaller number of valence electrons to lose or gain makes them more reactive. That's a delicious pattern, don't you think? 6 says, why does the location of the valence electrons near the nucleus affect the different reactivities of the halogens? Well, since the halogens all need to gain electrons, the one whose nucleus is closest to the valence energy level will be the most reactive, and it would be the smallest one. Right? Wouldn't the smallest atom have its nucleus closer to the valence electrons? So it can capture an electron faster due to its higher attractive force when the valence energy level is so close to the nucleus, the positively charged nucleus. Well, why does the location of the valence electrons far from the nucleus affect the different reactivities of the alkali metals? Well, they have 1 to lose, and in contrast to the halogens, it's easier for the alkali metals to lose the electron they must when it's farthest away from the nucleus and there's the least force of attraction. So those the faraway valence electron is looser and more likely to be lost from the atom. Looser because there's a lower force of attraction. All right. All right. So remember that you can stop the video whenever you need to think about something or you want to check something. And also remember that the thing you can do is put my screen half screen and your screen side by side. All right, so you can see what you wrote and what you understood. All right. Do you remember this one where we got out our ball and stick models again and we began to try and build 3-dimensional examples of what was actually happening when we did these Lewis dots? So here, all right, I picked these 2 Harpers to illustrate what they got for the 3-dimensional structure of these elements, all right? Yeah, very happy group. All right, so we were looking at hydrogen and hydrogen. Then we looked at hydrogen and fluorine, the Lewis dots. Excuse me for yawning. It's late at night. All right, hydrogen fluoride. And then hydrogen and oxygen, and then carbon and hydrogen, all right, then nitrogen and hydrogen. And we saw the Lewis dots, and in these, we saw that there was sharing going on. Let me get on the right. Somehow I've just lost my page. All right, here we are. So let me go down here where I think I wrote something. All right, I did. So what I wanted to do is talk to you about the fact that we showed covalent bonding first, in which 2 electrons are shared. All right? So we have nitrogen, and it has 1, 2, 3, 4, 5, 6. Oh, no, it only has 5. Forgive me. Did you catch me? Did you catch me? All right, so we can see it has 3. All right, and it would like to have another one. Now, the reason this is going to be an example of covalent bonding is because there's going to be sharing. Because in each of these instances, and I will get some, there, let's get some red. All right, a hydrogen will glom on with its single electron, and this hydrogen too, if they collide properly. All right, and then this hydrogen too. So it doesn't just give away its hydrogen, it moves in. All right, so hydrogen doesn't just give away its electron. Its electron. It moves in. It moves into the compound. All right? So see, that's why you can't just put the electron there without the whole hydrogen coming with it. Yeah, without the whole hydrogen coming with it. All right? And so these 2 electrons are shared. So this is where I drew something that had this shape of, oh, let me get another color of, remember I drew sort of a shared pea pod here to illustrate that these 2 were sharing, that the 2 electrons shared were in the overlap of the 2 atoms. All right, no ions are formed. All right, these are atoms. All right, so hydrogen doesn't just give away its electron, it moves into the compound, and that's what we see happens. All right, so then we have a nitrogen. Let's make it a purple. All right, so nitrogen is an atom, and each hydrogen is an atom, and they're sharing the electrons between them. All right, so this is how a covalent bond works. All right, so when I've done a lot of drawing, I think it's easier if I just give you several more examples and you actually see me drawing. All right, now we have hydrogen and oxygen. All right, so let's just write the Lewis dots of each. Oxygen. All right, 1, 2, 3, 4, 5, 6. All right, we can see that there is a need. There is a need to have another. All right, and hydrogen has the same problem, right? So that's why hydrogen's electron, which I'm going to make a different color. All right, so this one right here, yes, these 2 are going to move closer. All right, so what we're going to see is hydrogen, oxygen, and hydrogen, where they are sharing the electrons. All right, and then we'll give oxygen the rest. So hydrogen had 6 electrons, valence electrons. Hydrogen had 1 electron, and the other hydrogen has 1, and that's how now we have 8 electrons. So the 8 electrons, 1 from each hydrogen and 6 from the oxygen. All right, so that's where these 8, and now I'll put the peapod thing around them to indicate, all right, so between these 2 elements, whoops, that's not the right one, is it? That's already paired up. That's already paired up. Yeah, it's the other one here. There you go. And so that's when you see water, it actually looks like this, where the stick represents the single bond. The stick represents the 2 electrons, the shared pair of electrons. A pair is 2, right? And now what oxygen has around it is all these paired, but only 2 of them are shared. So that's why these are the covalent bonds. All right? Yeah. So there's 2 covalent bonds in water. All right, so covalent means sharing. Now, then we talked about ionic bonds. Oh, well, this is kind of different. This is kind of different. So let's put, it says potassium, all right, and iodine. Wait, that didn't look good, did it? All right. Well, now we see this is a different situation because this metal wants to lose it, doesn't it? Yes. So that's what's different over here. Hydrogen didn't want to lose it. It just wanted to share it. But the metals always want to lose. Metals want to lose an electron. Want to lose an electron, not share one. Not share an electron. Yeah. Because they're trying to get their full 8. So let's go. We'll give this electron now a new color. All right. So there's that electron that has moved out. Well, iodine wants to put one here, and it has a plus 53 charge. So it's going to come right out and get that and put it right in there. And now the difference here is iodine has 8 electrons in its valence shell. So iodine gained an extra electron, making it a -1 ion. Whereas potassium lost an electron, making it a +1 ion. So ionic bonds are about ions. All right, and so the key here is that the K+1 is highly attracted to the iodine -1 ion. Highly attracted. I left out the key word, didn't I? highly attracted to the I-1 ion. That's why they stick together. That's why these opposite ions stick together so well. Ta-da! All right, so that's the difference between ionic bonds, which create ions by transfer of electrons, versus covalent bonds, in which it's more convenient for sharing of electrons, two electrons between the atoms. Which is stronger? Oh my gosh! Ionic bonds are much stronger. Talk about a force of attraction. Yes. All right. Now, let's move to the next one, which is the lab we just did fairly recently on metals and nonmetals. So the first thing we did was look at, let me make this just a little bigger because I'm really putting it over the top of something else. We were talking about what are some important physical properties of elements, some important chemical properties, and how unique are these properties to metals versus nonmetals. All right, so first we were talking about physical properties where the value doesn't change the substance. For example, state of matter. All elements have three phases of matter. So it's still water whether it's frozen or whether it's water vapor, right? So there's no change in the element. There's no change in the element. There's no change in the element or compound. Here we were just talking about elements. In contrast, in chemical, there's actually a change. All right, let's look and see which ones were physical. Conductivity, yes. Dissolving in water, when you dissolve salt in water, you still have salt because you can taste it, right? Or sugar, you can taste it. Melting, yes. We're just talking about a substance that melts from a solid to a liquid state. What about color in the flame? Yes, that's an appearance thing. What about how magnetic it is? Yes, that's a physical property of iron. It doesn't require iron to be combined with something else. Boiling point, it's the same substance when it boils, because it's going from a liquid to a gas. All right, and the color of the compound, shininess, etc. These are all physical properties. Now, chemical properties are really quite different because you do get something different. When something burns in a chemical reaction, the ashes are a new product, and you've seen that many, many, many times, haven't you? When an acid reacts, there's something about an acid that is trying to change the other reactant and produce a new product. The other ones were adding a base, which we will see later when we do some precipitation reactions. And corrosion is an element because rust is a kind of corrosion. And you know something's happened to the iron because you know how when cars rust, after a while they get a hole in them, indicating the iron itself was eaten away. So the rust is a chemical reaction with oxygen that is facilitated by wetness. Why there's more rusting is snowy climates where the bottom of your car is often wet. And then there's salt on the road, scratching All right. So rusting is corrosion. So you made a list of physical and chemical properties, all right? And we went through this whole lab, and you'll want to look back again at what we said. So what I wanted to do was talk about the answers to these questions that you did. Oh my goodness, let's fix that. Okay, so what I want to do is just make these show up a little bit. All right, here we go. Now, what are some important physical properties of elements? How elements look in terms of shiny or not, granular or not, colored or not, are physical properties. How elements can be used depends on their malleability with tools versus their tendency to shatter when worked with. All right, so in industry or in the lab. A third important feature of elements is whether they conduct electricity and heat. If they don't conduct, this property is called, the element is an insulator. All right, it has insulative properties. All right, what are important chemical? Chemical properties are about the reactivity with other elements or compounds. We test elements with acid to see if there was evidence of reaction, and flammability is another important chemical property in which when you burn something, you can see that you have performed a chemical reaction because new things are there. All right, explain how the physical and chemical properties of metals are different from those of nonmetals. Well, we saw that metals are conductors of heat, electricity, while nonmetals are insulators. The opposite, poor conductors. Metals are generally malleable, whereas solid nonmetals are more brittle and tend to shatter. Even metalloids like silicon shattered when the teacher pounded it with a hammer when I was trying to get smaller pieces for you. Metals are shiny and most are grayish, while nonmetals are dull and may have a bright color like purple, red, black, or yellow. Purple, iodine, red, phosphorus, black, carbon, yellow, sulfur, etc. All nonmetals. Are their unique properties different enough to tell a metal from a nonmetal? Oh, yeah. Metals are easily identified due to their hard and shiny appearance and conductivity. That's enough to say, if it doesn't look shiny and have this hard appearance and some conductivity, it's not a metal. All right. What are 3 ways to tell if a chemical reaction occurs? Well, we saw bubbling. You smelled a stinky gas, didn't you? We saw a different colored product, all of which indicate a chemical reaction occurred. All right. Now, the next lab we did was this one. Oh my goodness, let's make this bigger, in which we were comparing the reactivities of metals. And the way that we tested it was to combine it with acid. All right, and that's because we were using transition metals. We saw that alkali metals will react with water, and so will alkaline earth, the majority of them. But the transition metals only react with acid. So I had to use acid so we could get the most reaction possible, and it worked, didn't it? Yeah, we saw some really good reactions, and you were able to do a very good job. All right, so what we saw happen was that sodium, when it reacted with water, means it can push the hydrogen out of the compound. So that's why this is called hydrogen displacement. It pushes that hydrogen right out. It's so reactive and takes its place in the compound. So hydrogen out becomes hydrogen metal all by itself. Hydrogen gas by itself. And the correct formula for hydrogen gas is H2. And then when the sodium takes its place, we end up with sodium hydroxide as the compound. And that's like lye. It's very corrosive. All right, so the whole idea of these reactions is if they're reactive enough, they'll push the hydrogen out of the compound and take their place. And then we should smell this stinky hydrogen gas as well as see it, as you did. many times. So we wanted to see which metal was the most reactive. So let's get down here. So here's what you said. That copper, which was doing nothing, there was no smoke, no bubbling, no change. You said there was no reaction. So you said it was the least reactive. Whereas you said the most reactive, super fast, smoke, bubbles. You gave that a 1 for the most reactive. All right, and then, even then, you were actually good at figuring out that aluminum was more reactive than zinc, which was more reactive than iron. And here's an example of someone's plate that I captured where you could see the labeled reactions. And we saw that copper just did next to nothing. It just moved around with the flow of the acid. Whereas the rest of these we can see are really very different after the reaction. Yeah, you can't even see any metal, can you? Except you kind of can in this piece. You can see some magnesium, but I think it reacted so fast it ran out of acid. It would have kept going. All right, so you entered your ratings, and which metal is most reactive, and you figured out magnesium was most, copper was least, and then you figured out, so we had most reactive magnesium, least reactive copper, and then you said the order was aluminum, zinc, and then iron. And then we went over here, you copied this reactivity series from me, and we saw, oh my goodness, we got exactly the same order. Yes, where the most reactive was magnesium, then aluminum. So everybody who had done this got the same results we did. Wow. And we saw, too, that the metals that tarnish with air are all the way from the most reactive to silver. All right? So if they react with air, we call that tarnishing because they change color. They've reacted with air to form a new compound that's an oxide. A lot of oxides are blackish, metal oxides. Then we saw that all the way down to lead, these guys will react with acids. But these guys do not react with acid. Yes, so now we realize why copper didn't react. No, it's not reactive enough. Notice hydrogen is more reactive than this is. So neither hydrogen or mercury nor even silver are able to push the hydrogen out of HCl, nor would gold or platinum be. All right. So, and the only ones that react with water were about down to sodium, so the most reactive. Magnesium reacts with very hot water, but that wasn't worth testing. We might as well go after the big reaction, which would be with acid, and that's the one you saw. So, what we were doing here was figuring out what were our results. So, of the 5 metals, we found magnesium was most reactive. That matches the chart. We found copper to be the least reactive. Copper is lowest on the chart as well. We said aluminum was more reactive than zinc, which was more reactive than iron, and the chart matched this order as well. So we were pretty hot stuff in this lab on reactivities. All right, then we were doing all of this kind of fun stuff. Remember, Miss Frizzle took you down to the atomic level, where you could actually look at the particles. And I said we were hanging in like a shark cage, you know, those things that you can go down and watch the sharks, but you're safe from them. So it's as if we were one of those, and these particles were going crazy all around us, and we were safe in our special vehicle to keep us safe at the atomic level and not attacked by these particles themselves. All right, so we saw that these these reactions depended on successful collisions. So the more collisions you have, the more likely there will be a successful collision. And the higher the energy the collision is, the more likely it will happen, because we discovered it turns out that there's some mountain for these to climb. That not only does the collision have to happen in the right orientation, how they collide, but there has to be enough energy in the collision for it to actually happen, and each reaction has a different mountain. This mountain was called the activation energy. All right, so then we had these to do. All right, so let's look. And all right, so explain what a reaction rate is. Well, a rate is the speed of something happening over time. So therefore, a reaction rate is the speed of a reaction occurring over time. This is usually measured in two ways, whichever is the easiest. How fast the reactants are used up, or how fast a product is formed. That makes sense, doesn't it? So we're actually catching the new product that's formed, or paying attention to how much reactant is missing. All right, so that's how we would measure a reaction rate. Explain what particles are doing when they react. Well, when particles react, it means they ran into each other at high speed and were oriented in the right way and with enough energy to have a successful collision. Successful collisions don't happen with everyone. Many collisions are required to make sure products will form successfully and in a shorter amount of time. Ideally, when we want reactions to happen, we want them to be faster. When we don't want reactions to happen like rusting, we want them to go slower. All right? So we can use the ideas we learned in this to either make a reaction occur faster, or to not provide the right collisions or the right possibilities to have corrosion occur at a slower rate. Explain what happens to chemical bonds when reactions occur. Well, the bonds holding the reactant particles together break, just like the bond between the two hydrogens and oxygen had to break before the new bonds in water could be formed. Remember, those were two oxygen-hydrogen bonds for each water particle. If you don't remember, you can go up and look at that picture again. What three factors increase the number of particles to collide? Well, the more particles that collide increases the likelihood of having a successful reaction. So decreasing the volume allows the particles to get closer together and collide more, also increasing the likelihood of a successful collision. So we can change the volume, or we can simply add more particles to the same size container. In addition, increasing the availability of the particles increases collisions. For example, dissolving the solid in solutions spreads the particles out for better collisions. So this is what we're going to be doing in the precipitation reactions. You're going to see that they react very rapidly because they're so available in the solution, the ions having been spread out in the dissolving process. Increasing the surface area of the substance means more particles are available to react. For example, granular rather than sheet, or cutting into smaller pieces. All right, we saw that there was better reaction with the metals when I made them more granular than when I had copper on sheets. So even if I had had copper in the granular ones, it would not have reacted. But by putting the other metals, zinc, aluminum, etc., in a more granular way, you could see a better reaction, and that's why I did that. Should have a better reaction rate. All right, and I think you saw that for the most part, the reaction rates were while they weren't the same, were fairly quick. What factor increases the number of high energy collisions? A higher temperature increases the speed of particle motion and therefore leads to higher energy collisions among particles. More collisions and more higher energy collisions increases the chance of successful collisions. Now, 5, explain what an activation energy means for a reaction. Well, Activation energy tells us how energetic the collision has to be to lead to a successful production of products. In that diagram I just showed you, it looked like a mountain the reactant particles have to climb to reach a high enough energetic collision. All right, they have to get over that threshold to a reaction. All right, now to precipitate or not to precipitate. All right, so this is the one where I gave you many solutions and you had to decide which ones to pour together. And the way you decided that was by the activity series of metals. I don't know where that went. Give me a second to go get it. Maybe it's in the first hour. There it is. Let me go grab that. All right. All right, so the solubility rules chart, let me make this as big as possible. All right, it shows the metals across the top. So lithium, sodium, potassium, the alkali metals, then the alkaline earth metals, then the transition metals, and then lead and aluminum are post-transition metals, as is tin. All right, so we saw that when they were in a compound, then with one of the negative non-metal ions, all right, so these were non-metal ions. And these are metal ions. I need another color. All right, these are metal ions. All right, so in a compound, ionic compound, we're going to have a metal and a non-metal. All right, so we can see that if you put lithium with chloride, lithium chloride, you would get a soluble solution. And that meant no precipitate, PPT. All right, we use for precipitate. So if it dissolves, there's no precipitates. All right, then we saw, let's look for something that's insoluble. It turns out if a compound forms of magnesium with fluoride, it's insoluble. That means that the precipitate forms. All right, so that's what you were looking for when you were predicting which reactions you wanted to run with these possibilities. I think I added to this sodium fluoride as well. All right. All right, so you did all the predictions. So this was you using your knowledge from the solubility chart to decide which things you wanted to pour together. All right, so the procedure, etc. I wanted to know how rapidly these occurred because they're in solution, so they should happen very fast, right? And explain how many of your predictions were correct. And if wrong, what kind of mistake did you make? Well, let's look at, let's go ahead and show these. All right. First question, how do we know if a precipitate will form or the container will stay clear after we pour them together? Well, certain combination in elements in solution will form a compound that won't dissolve. So the product, when forms, falls out of solution. We call that cloudiness and subsequent drop to the bottom of the container a precipitate, PPT. The solubility table enables us to predict which combinations will precipitate when the compounds exchange partners. Well, how do we determine the chemical identity if some precipitate does form? Well, we know what precipitate should be from the two compounds in solution that we mix together from the solubility chart, right? It's the solubility chart that tells us which of the two things. Which metal and nonmetal combined that made the precipitate? How can we draw a beaker picture? Well, the beaker picture indicates the reactants and enables us to figure out how they would exchange partners in the successful reaction. So let's just do one up here as a reminder. All right, so let's say we have NaF here, sodium fluoride, and then we have MgCl2 here. All right, now, when these go together, sodium and chlorine would form, and magnesium and fluoride would form. All right, so we should get sodium chloride and magnesium fluoride. All right, now we just go see. Oh, I think we saw that magnesium fluoride is right here. It does not dissolve, whereas sodium chloride is soluble. NaCl does dissolve. All right, so let's go back. This is soluble, which means it dissolves in water. Whereas this guy is insoluble. When it forms in the reaction, it clouds up the solution because it can't dissolve. All right, so that's what we did there. The beaker picture indicated those reactants. So how did the precipitates differ in how they looked? Well, some were creamy in color, yellow, some were dark, some were fine, stringy looking things, others were clouds, others just looked like snow beginning and piling up. So would you say that covers it, what you saw? So it depends on which ones you chose, since you had a choice in who you wanted to pour together. So some of you may have gotten more yellow or creamy. Others may have gotten more dark ones, depending on which solutions you poured together and which precipitates, which compounds were precipitating out. All right, so that's everything we had covered. So on the test, you would definitely have a solubility chart if I ask you anything about it. All right, and of course, you'll always have your periodic table. All right, now this was pretty long. It's a whole class period, but that's okay because I'm giving you a whole class period. All right, so I want you to do the very, very best. All right, trust your intelligence. And remember, I always want you to think. All right, my best to all of you. Adios.